British box sets from the BBC.
Oh, go away, Sean. Fuck shit. Get on.
How much does this thing weigh?
Well, try and pick it up.
Okay.
Okay.
Alright.
Yeah. Be nice to
105 pounds.
105 pounds.
It consists of 4 motors connected up to these spinning magnet arrays. And if you spin these fast enough, it will actually levitate.
That's correct.
Let's see if it can do it.
Are you ready? Let's fire it up.
It's lifting!
Okay, it's flying now.
Is it?
Yeah, go for it.
Now it is so easy to just move around. That's amazing.
Give it a push, like it's got some real...
Wow. It can carry some weight, hey?
Yeah.
That is amazing.
So how does it work? Well, it's similar to how a magnet falling through a pipe is slowed down. Anytime a conductor experiences a changing magnetic field, electric currents are induced in it which create a magnetic field to oppose that change. And in this case, the spinning magnets induce currents in the copper sheet. They create a magnetic field which is nearly a mirror image of the spinning magnets, and so they're repelled. If the rotors spin fast enough, this repulsion leads to levitation.
That is awesome.
Alright, let's set it down here.
Yep.
So it's just going to come gently land.
The induced currents then encounter resistance in the copper, so they dissipate their energy as heat.
Whoa. And this copper is pretty hot.
It's gotten warmer. Yeah, I can still keep my hand on it, at least for a second or two.
But it is like a hot.
Except with this one, the changing magnetic field was created by an electromagnet in the base, inducing currents in a light aluminum plate, which levitated. Whoa! The plate got so hot, you could boil water on it.
Check out how hot this plate is. If you have 2 north magnets facing each other, they normally just kind of like fall off.
Yeah.
Is there a similar problem here or no?
Not really, no. And the reason is the magnetic fields that are induced by currents in the copper sheet are a mirror image of the applied magnetic field, and the effect is so quick that as it moves, it just kind of follows it around.
Making this device work in practice is harder than it looks. For one thing, the magnetic field of the permanent magnets has to be very strong. Neodymium magnets are strong, but there's a special configuration you can use to make them even stronger.
It's called a Hobart array. They're used in particle cell arrays. They're used in fridge magnets, actually. As arrays, they're so long as that.
Magnetic field lines run from north to south, and they're normally symmetric on both sides of a magnet. But if you rearrange them like this, the magnetic field lines are channeled almost entirely into one side of the magnetic array, and they cancel out on the other side. This configuration produces a much stronger magnetic field without changing the properties of the magnets. In these rotors, there are 12 wedge-shaped magnets. Their magnetic poles are fixed in this particular arrangement. This increases the magnetic field on the bottom side and almost eliminates it on the top. As the magnets spin, they create a rotating magnetic field in the copper beneath them. This induces currents that create magnetic fields, which oppose the magnetic field of the spinning magnets above. The result is a repulsive force that is effectively lift for this quadcopter. But in addition to lift, there is also drag. Energy is clearly being dissipated in the system as the heat produced by the induced currents in the copper. And that energy comes from the fact the magnetic field of the induced currents is not a perfect mirror of the spinning magnets above. Instead, the induced magnetic poles are slightly ahead, so they produce a backward force on the rotors, which is really a backwards torque.
Wow.
And that's why the rotors on alternate corners have to spin in opposite directions, because otherwise they would produce a net spin and turn the whole machine in one direction. This way, they cancel out. This principle has been used to achieve levitation in everything from maglev trains to hoverboards, and it's being considered as a means to make the Hyperloop, a superfast system for transporting people and goods through tubes at very low pressure.
Sorry.
But instead of spinning the magnet, the vehicle's motion itself would cause the magnetic field to change in the conductive track below.
So in the future, you think this is going to be how we travel?
I think like ongoing developments in digital motor controllers and very powerful magnets will mean that talking about moving humans and cargo at extremely high speeds is actually something that we can, as a species, kind of look at. Wow, it turns out that getting from one city to another city in the same day is something that the next billion or 2 billion people might have the opportunity to do in one lifetime.